Good afternoon, and thank you for joining our talk on solutions to common edge issues. My name is Mikhail Kazurvitsky, and I'm a consulting engineer with Rancher Labs. By day, I specialize in helping our customers with their edge and embedded solutions. So let's get started. So I've worked on the edge even before Kubernetes, deploying batch kiosks and managing them at hospitals, deploying software to data centers at ships that have to transmit terabytes of data back to the data center, to POS terminals that you'd find in your restaurant or grocery store, and as well as mobile contest signups that you could find at Daytona or concert venues. So, and I've been a part of many of these successful implementations with and without Kubernetes, and of course a few failures, and I want to share my experience, so hopefully this journey will be easier for you. And of course we're going to be at the edge, and I hope I can call you my friends. So the edge before Kubernetes had a little bit less overhead. It was a dark place with also less functionality. The edge with Kubernetes has a little more overhead because now we're running this sophisticated orchestration platform. But that also means we have better reusability. We can use the same workloads as we do in the cloud as long as they have the same resource requirements. And we can offer more functionality, like scheduling that's built into Kubernetes or node management. So this extra layer that Kubernetes adds, there's a cost. Not just in raw processing power overhead, but also in sophistication. And it doesn't make sense to use that without taking full advantage of it, both in your applications and your processes. And so, but to determine really what we need to have at the edge and what issues we're going to face, we really need to break down our use cases. And I broke them down into these three categories, but you could break them down in other ways. And your workloads may fit into many of them. So first is collecting and sending, right? So what I mean by collecting and sending is where we take data from like a single sensor, like a windmill or a temperature sensor, and we send it out to the cloud or our on-prem location for processing. Or we are taking multi-sensor data, or perhaps then all the sensor data for one location and piping it together to send to our processing location. And we may be doing that in real time, or we may be batching it depending on our connectivity or regulatory requirements. We could also be processing data, machine learning, analytics, alerting. Right? We could be doing real work, which requires processing power. And we might be controlling some hardware, maybe a press in a factory or LED lights on a sign, and handling user input more like a kiosk, where we're taking credit card data or taking in a person's name or an email address. So all those have really different considerations that we have to think about. So in different challenges, and I broke down our challenges in really four areas that I'm going to talk about: connectivity, architecture, size, and scale. And I'll tell you a little bit more about each one now. The connectivity is like air-gapped, semi-connected, or fully connected. If we're in an air-gapped environment, whether for regulatory, security, or other reasons, we have a whole lot more considerations we have to worry about, because it's just hard to do anything from a management or deployment standpoint. In semi-connected devices, we at least can sometimes connect to the device, and there you can use strategies like edge-driven configuration management through like Fleet, or used to be on machine through Chef, where the edge doesn't need to be told by the central system what to do. It goes out when it connects and it checks itself, right? It also lets you get around firewalls and lack of inbound connections. And then you have fully connected machines that for all intents and purposes are like your on-prem data centers. They are their own data center, and for those you have other things to consider like security. So the next category is architecture, and the reason why I put it in a category by itself because I think this is a huge, a huge component that needs to be considered. Whether you're going to develop on ARM or x86, with Apple migrating developers to ARM, it is the future. It is also way more power efficient. I think they said something like 50% more power efficient than x86, and that's huge. Apple uses these ARM chips. They're RISC chips, so they do a lot less per cycle, but they take a lot less power and they do it a lot faster, right? Whereas x86 does a lot of things. They use the CISC, which is the sophisticated instruction set. They can do a lot more per cycle, but slower. But more power consumption. And then there are sizing considerations, like is this a small device like an Atom machine, or or something even smaller like an ESP32, or is it a medium machine? And what I mean by medium machine, it's more like it could be a Windows box, right? Like a ATM or a desktop. And what I mean, the next size is large, and really large is more like a rack, or where you have multi-node, you have an entire data center almost. And then scale. And here, I talk about, I mentioned mostly manual and mostly automated, but the reality is we should never be doing the first one. So we're not even going to cover the issues with that because it's such bad practice. And we'll talk about, what happens when you're mostly automated and hopefully operating, using GitOps and really scalable processes. So when we break down the different connectivity issues, you're really talking about inability to transmit out for air-gapped. Really everything is hard to do in air-gapped, like I mentioned. You can't transmit out, it's hard to deploy and update, and it's hard to test. For semi-connected workloads, you don't really know your central state. You also have a hard time updating and deploying, and your speed could be inconsistent. And then for fully connected devices, you obviously have security. And security is a big issue on that one. But it's really an issue for all of them. So for deployment and updating in an air-gapped environment, you can preload the images locally by either running a Docker registry or some kind of registry and chart museum, or loading them on the device prior to shipment. And importing, so K3s allows you on startup to load images and manifest or Helm charts directly into the system. You could also use a microservice to allow people to upload it through a web interface. But in the end, it's still going to have to go to either a local registry or get loaded directly into your container runtime, like Containerd or Docker both support. And then when you do testing, you can use your set proper network rules on your cloud environments to simulate. You're still going to have to use some kind of bastion host or something along those lines, but you can recreate it, and you definitely should before it goes out, because you will never really know what issues you're going to face until you replicate that as much as you can. For the semi-connected workloads, we're dealing with a few other issues, right? We're still dealing with connectivity issues, but more so that we don't always know what the state of the edge is, right? We may be at, the ship may be at port one day and gone the next, or, our truck may be offline that has our infrastructure on it, and we can't really depend on that. So you really have to use the edge-driven technologies to manage those updates. What I mean is that the edge machine sits there and says, hey, I need to check the state. And then it connects back to your home server and gets the new state and tells the server what its state is, and then disconnects and does its thing. And then connects to GitHub if it finds anything that it needs to update, and loads the latest, or in the case of Fleet that I'm talking about specifically here, and the Rancher's continuous delivery, it can import customized Helm charts or manifests. So we do believe the best application unit for Kubernetes is a Helm chart, but depending on your environment, you can, or the package, you can use manifest and customize as well. So as far as speed goes, you know, you can batch your workloads and compress them, as well as continuously check for that connection before sending. So make sure that you have a connection, compress your workloads, and batch it out when needed, right? Unless you need that real-time data. And if you do that, you probably need to be in a fully connected environment. So lastly, let's talk about security, right? This is a really important topic that we can't skimp on. So for security, you should be deploying firewalls. In a zero trust environment, you should have firewalls everywhere, and in this case, it's no different. The edge is just whereas the cloud is someone else's computer, the edge is your computer that you can't touch, and that doesn't make it any more fun. And inside Kubernetes, you can use network policy to limit interaction between workloads, as well as intrusion systems, right? You can also block inbound access unless it's really required by utilizing that edge-driven check-ins for your updates. So it's effective not just for semi-connected or disconnected environments. You should also ensure that your data is fully encrypted in transit outside of your cluster, right? You should not be sending HTTP requests to your data center, and use TLS. So you can also use you should be using restrictive pod security policies, so that if there is an update to an application or a new application gets deployed, it has very limited access to your cluster. And this is super important because once someone gets your cluster token from any single node, it compromises your entire cluster. So restricting that to applications that get deployed pre-startup is really recommended. And then you can utilize OPA to validate that both your current applications and the new ones meet your security standards. And OPA is a open source project that recently GA'd, and it's excellent for building policies. You should also be scanning your images, whether you're deploying to the cloud or the edge. But for the edge especially, because it's harder to check what's currently running in your cluster, you should be keeping those images while they're deployed, so that even if you can't connect to the edge device, you can still know when you have vulnerabilities and trigger your update process, no matter what that is. And in general, you should be using best practices, including running CIS scans. And the CIS scans will tell you, if you're doing something wrong. Sorry about that if you couldn't see that. So when talking about architecture, really the issue with x86 is power consumption. And until recently, it wasn't even an issue, right? 10 years ago, everything was x86. When we needed low power items, we were talking about Atom processors. But ARM chips have gotten so advanced, even Apple is switching developers to them. And, my Raspberry Pi cluster at home is running ARM as well. But that brings us to some challenges. Those ARM clusters, they're hard to develop for when you have a x86 machine. And that's why not everybody does them. So a lot of popular common libraries like Bitnami's don't have images available in ARM. And that presents a lot of issues when you need to deploy fast, or you expect something to work and it doesn't. Even Rancher's monitoring 2 right now doesn't run in ARM. I'm sure we'll change that if we can, but our upstream projects, Prometheus, also don't have ARM builds released, and so they may mean that there's a hardware requirement that makes it more difficult. But in the the power issue on x86, unless you need low power stuff, it's x86 still the way to go, because you're not going to run into any of those build issues that I just mentioned. Now, those aren't inconquerable, but they do require some effort, right? So for example, how do you develop on x86 and deploy to ARM? So there are 2 strategies that I've used in the past that work pretty well. You can run your pipeline on an ARM architecture. So your CI pipelines, a lot of the commercial ones now come with the ability to run in ARM architectures, or like in the example of GitLabs, you can deploy that on your own ARM cluster, or you can deploy using a BuildX. And BuildX is instead of using Docker build, you can use Docker BuildX, and that allows you to do multi-architecture builds to upload to your repository. So, and before you go off on your cloud, make sure that the tools that you're wanting to use either have ARM versions, or that your team is capable of building them in case it's needed, right? And this should all be tested out, obviously. But let's move on to sizing. And with sizing, right, you have different issues depending on the size of your deployment. With small devices, the biggest issue is resource limitations, trying to do too much and not really understanding that before the device ships out. So for that, you really need to do really good testing and stress the device to whatever the maximum that it will be stressed on location, and run that for a consistent amount of time. For medium devices, you have the legacy workloads that I mentioned about, right? How do we handle these Windows things that need to run but scare us to death? How do we make sure that when they fail that we can reboot them and do that automatically without losing our ability to operate? And then with large devices, you have large node configuration issues and multi-node configuration issues, right? When you're talking about a data center, you may have multiple nodes there. And dynamic provisioning, right? How do you migrate applications in a multi-node environment? And so when we deal with the edge considerations for small sizes, resource limitations are the primary one. And I kind of mentioned some of the things you can do, but also use a minimalist OS. Something like K3S as our minimalist Kubernetes version can also help slim down on what's happening. And one thing I didn't mention on here, but I think it's really helpful, is our K3S update operator that allows you to update K3OS through Kubernetes CRD. And so something like this, combined with our VM manager that I'll talk about in a second, will allow you to have one control plane. And really, to me, that's the grand vision, right? One place to know everything that's going on with your edge device, and one place to make changes. And so like I mentioned a second ago, for the medium size edge devices, the biggest issue is legacy workloads. How do you utilize those Windows VMs to throw your application in there, isolate it? Well, I mean, that's how you do it. And then deploy the strangler pattern, to basically put yourself between it and any of your other applications, and monitor it, right? Make sure it's responding, and if it needs to be rebooted, the VM can be rebooted. And we have a tool for KubeVirt. So KubeVirt is a Kubernetes tool that allows you to manage VMs, and we've built a UI layer in Rancher with it, and created a tool called Harvester. And Harvester, allows you through CRDs like KubeVirt to manage those virtual machines. So, completing that process of creating a single control plane to manage the entire edge installation. So, when we talk about large nodes, the biggest issues are the dynamic provisioning. I put that, I changed the wording a little bit on this slide for dynamic node provisioning, but really its provisioning of everything is difficult. For the large node configuration, by default, Kubernetes has a 110 pod per node limit. You definitely need to change that by changing your networking CRD subnet value that you allow, a higher slash value will allow you to utilize more IP addresses for your overlay network, and allow you to put more pods on that node, because if you have something like 40 or 100 different CPUs and a few hundred gigs of RAM, that 110 pod limit can be a real limitation. And then for these larger installations, you also may have multi-nodes, right? You may be able to do HA. You may be able to divide your workloads. And from there, making sure that your workload is on the right node can be difficult. And so you can make sure that you're scheduling correctly by using nodes and taints. And you can also do this when a certain node has certain hardware features, for example, a GPU that you need to use for machine learning. You can do that through setting a taint on that node, that only things that require a GPU or that have a tolerance for GPU are on there. And you can use softer rules like affinity on the individual workloads to prefer certain nodes if they exist, or look for certain labels that may or may not exist. But still allow scheduling on other nodes if no matching nodes are found. All right. Well, so the last item that I want to cover is scale. And what I really mean by scale is automation. How automated are you? If you're mostly manual, you really don't need to be deploying things to the edge. The edge is hard to get to, hard to control, update. So get your stuff together. So we're not really going to cover the issues with that because there are way too many. And I would say I have personal experience with this. When working on a large number of support physical devices, the most expensive thing you can do is get out there, right? And in some cases, you can't even get out there. If your node is at the bottom of the ocean, you're not going to get there. So high optimization, high automation are really required. But even then, in order to do that, you're gonna deal with those core system upgradability issues and workload upgradability issues, as well as observability. And you're gonna deal with them for different reasons. So with the core system upgradabilities, if you're running Kubernetes, you really don't want to manage anything else. So fixing that is quite important. Then with the updatability, like I said, the thing may be at the bottom of the ocean. So updating that workload requires either connection, physical presence, or other. And then observability. And this, you can deploy the standard, if you're on x86, you can deploy the standard observability tools, and I'd recommend doing that. You also need to ship off your monitoring data, like if you're using Prometheus, back to your cloud so you can have that accessible and in case something happens. But let's get into this more detail. Whoops. Oh, one slide too far. All right, so deploying without upgradability for core systems. So this you solve by using Kubernetes. We have an updater that allows you to update operating system components. It can be modified to work with your use case, and using something like that will allow you to just use Kubernetes and update through the Kubernetes API. And if you're using something like a Fleet from Rancher, then you're able to do that whenever the machine connects back, right? So you don't have to have full connectivity. Now, if you're in an air-gapped environment, you're going to have to send someone anyway. So that's why those other things are so crucial. And then, upgrading workloads is very similar. If you're regulated, air-gapped, someone has to be on location, so you have to give them a way to update, right? Whether that's a simple web service that's running, or whether that's a temporary remote access, or a tech that knows what they're doing, comes out and shells into the machine. So for observability, like I mentioned briefly, if you're on ARM, make sure you have images available or create your own observability to monitor your golden signals. And if you're in a semi at least connected environment, you can do on x86, you can do standard monitoring and then have batched uploads of your monitoring data whenever you have a connection. So thank you guys for joining me. Those are the main issues I think that we deal with on the edge, and really how to get around them. But the key is to know your needs, tailor your solution for minimal issues while doing as much for you as possible, right? Let's utilize all the great Kubernetes functionality. And that way you can spend your time working on things that return an ROI, that differentiate you from your competitors. And it's everyone's responsibility. So because there's so many things involved in doing this, your engineers, your project team, your business requirements, and the finances that are available for this project, all this information really needs to be shared among the group so that your engineers can understand the business requirements and the cost that you can absorb, so they understand the type of hardware that can be deployed. All that information and the clear communication of it is really required for a successful project, and especially the communication. So if you have any questions or comments, well, we're going to stick around here for another 15 minutes or so. So I'd love for y'all to ask me questions. Thank you for coming. You could also email me, connect on Twitter or LinkedIn. Thank y'all, and I hope y'all have an awesome day.